The 21st century has seen unprecedented amounts of plastic waste in the environment, a result of exponentially increasing production quantities and consumer demand. In spring 2022, we, a small group of students at Colorado School of Mines, were tasked with developing a prototype-level device to reduce the size of crushed plastic, a vital step in the process of reusing waste plastic and reducing pollution.
The linear economy of plastic, from resource extraction to processing to manufacturing to disposal, poses a major environmental problem. Plastics that aren't recycled end up in oceans and landfills. To solve this problem, plastic can be reduced in size, melted, and reformed into a new product, extending the life cycle of plastic products.
The objective of our project is to accept 1 to 3 centimeter size chunks of plastic and reduce the size to 2 to 3 millimeters. The design should be compatible with recycling plastics 1 and 2 as well as PLA. Overall, it should operate reliably without jamming and run quickly and efficiently while remaining portable.
We came up with 7 basic constraints for this design project. Our budget was $200. We had a finite amount of time to complete this. We needed to have it done within the semester-long class. The machine needed to use a standard outlet for power. The portability of the design was important to us for transportation purposes. We needed to create a pourable output size. The project goal was to shear the plastic, not melt it. This meant our operating temperature needed to be below 110 degrees Celsius, and the runtime of the machine should be reasonable, so within 5 minutes.
This was the final CAD model that we based our finished prototype off of. It was designed roughly based off of commercial granulators available, and we used two-bladed design that interacts with a fixed blade to cut the plastic. We ended up having multiple iterations of this CAD model as we were changing things as we built and tested to help refine our design to make it work more smoothly. The manufacturing of our prototype was split into multiple sub-assemblies, mainly including the frame, the blades, and the housing of the device. We used multiple techniques, including milling and welding, to help create the finished prototype.
Shown here, plastic is inserted into the granulator, at which point we use slow motion analysis to validate function.
In this shot, we see the plastic is forced through the small clearance between the rotating and fixed blades so that its size is reduced until it's fine enough to fall through the grate.
This video demonstrates the machine's operating noise level while running through all 3 types of plastic, PLA Type 1 and Type 2.
Shown here is the incredibly fine nature of our granulator's output.
The final prototype takes in plastics Type 1 and 2 and PLA through the funnel. The plastic is sheared between rotating and stationary blades powered by a handheld drill. The reduced plastic falls through the grate at the bottom once it is reduced down to about 2 to 3 millimeters.
Overall, the final prototype performs excellently in relation to the initial goals and constraints set by the team. The only shortfall of our final prototype is that the output produced does not pass the ASTM 1895-17 standard for pourability.